Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 8, Lesson 5, Linear, Exponential, and Quadratic Models. After this lesson, you'll be able to look at data and determine whether a linear, an exponential, or a quadratic function best represents that data. For the model and discuss, we have this table. We have the time in years. This is our input, so our x values, and our output would be just the value of the bike after so many years. And JC came up with a function that looks linear. Okay, so she came up with a linear function. And Emma came up with an exponential function. Okay, so remember the basic formula, A, the initial value, times the growth rate with the x and the exponent. And then for the linear, it's just mx plus b, where b is the initial value. So both of them are correct in the initial value. We start off with a value of $500 when you first bought the bike. So that's correct. But they have different rates. For JC, if it's linear, then it's decreasing by $14.20 every year. For Emma, since it's exponential, that means it's multiplying or it's decreasing by a percentage every year. And so then it's losing 15% since it's being multiplied by 85% over and over again. So this is exponential decay, losing 15% of the value. Who is more correct? So if you remember, if we're looking at a linear function, we want to know what's the change. We should have a constant rate of change. So just as we look at the rate of change going through each row in our data table. So the first one going from 500 to 485.20, we decrease by $14.80. Going to the next interval from 485.20 to 472.13, we decrease by $13.07. For the next interval, the next decrease from year 2 to year 3, we decrease by $11.13. And finally, from year 3 to year 4, we decrease by $8.90. So not really a constant rate. They're not really close either. We have kind of a big change going from 8.9 to 14.8. Let's take a look at the exponential function. So remember, if we are looking for an exponential function, we're looking for a common ratio, not a common difference. So what are we multiplying by from year to year? Well, if we divide 485.20 by 500, we're multiplying by 0.9704. Okay, I'm just going to go 2 decimals. And for the next year, from year 1 to year 2, so I divide 472.13 by 485.20, we're going to multiply by 0.9731, so a little bit more. And then for year 2 to year 3, we multiply by 0.9764, so a little bit more still, but still pretty close. We're around 97%. And the last year, going from year 3 to year 4, we are multiplying by 0.9807. So a little bit more, but really close. Looks like we are sticking around 97, 98%. So you're losing just a few percent every year. So which one is closer? Well, an exponential function is closer, okay? Even though I don't know if I would have that growth rate. So even though we're more consistent with our common ratio, it's not matching her function. It's not matching the decay rate that she wrote. But if we look at JC's rate of change, losing $14, that's closer. So even though I would say an exponential function is a better fit, JC wrote a closer equation, right? Her equation is closer to fit the data because Emma's function said it should lose 15%, and really it's only losing a couple percent every time. So we want to find out strategies to make sure we are coming up with the best equation that best models the data. We want our numbers to be the most accurate. Example 1, how can we determine whether the data in the table should be modeled by a linear function? So the first step you're going to go through when you have a data set and you want to determine is it going to be linear, exponential, or quadratic, then you want to start with linear because we're just looking for a common difference. We want a constant rate or relatively close to the same constant rate. So you're going to look for change in your x and your changes in your y. Remember, linear slope is rate of change. It's m equals the change in y over change of x. So if your change of x is equal to 1, that's easy. Then you're just looking for the first difference, the common difference. So if you have a constant first difference, that's your clue that it is linear. So we can see we are adding 2 each time. That should be your clue that it is linear. If you have a constant first difference. What if you don't have a common first difference? So if we look in our next example, our x values are increasing by 1, so that's good. Look at our y values. We're increasing by 6, we added 10, we added 14, we added 18. So it's not a common first difference. You might think this isn't linear, so then what could it be? Well, there's something called the second difference. So then we're going to check the difference of the differences. So now you're just going to say, well, what's the difference from 6 to 10? The difference is 4. What's the difference from 10 to 14? The difference is 4. What's the difference from 14 to 18? The distance is 4. This is called the second difference, okay? And this is the change in the rate of change. So how is the rate of change changing? If you remember our quadratic functions, let's see if I can draw it really quick. We would have this curve, and the slope represents a point on the line, and the slope does change, but if it's changing at a constant rate, then that's your clue that it's quadratic. So if you have a constant second difference, then you know that your data represents a quadratic function. Okay, so that's your first and second step. First, check the first difference. If you have a constant rate of change in your first difference, you know it's linear. If you don't have that, check the difference of the differences, check the second difference. And if you have a constant second difference, or relatively close, then you know it's quadratic because your rate of change is changing at the same rate. So what if neither the first difference or the second difference are constant? Well, then we're going to look for the common ratios. That's where you're going to look for what do you multiply by to get to the next value. So that then you're just checking what do you multiply by to get to the next y value. And that's how we're checking our exponential functions. So you're looking for your multiplier, your factor. So you can take your second y value, divide the previous y value, and you'll get the ratio. And if you have a constant ratio, we know this, a common ratio, then we know it's exponential. And you would write your function as initial value times the growth rate or decay rate with x in the exponent. So again, exponential functions is your last choice, your last check if you don't have a first difference or a second difference that's constant. Then you check the ratio. So let's try it. What type of function will model these tables? So let's first check our first difference. Going from -2 to -5, I'm subtracting 3. And then I'm subtracting 9. So I know it's not a first difference. It's not linear. So let's keep checking. This is going to be subtracting 15 and then subtracting 21. Let's check our second differences. So what's the difference to go from -3 to -9? My difference is 6. If I'm going from -9 to -15, what's my difference? -6. If I'm going from -15 to -21, what's my difference? -6. So I have a constant second difference, therefore it is quadratic. Let's check part B. So again, start with linear. What's your change? So I'm adding 8, then I'm adding 24. Okay, so it's not linear. Let's keep going though, because we're going to want to check the second differences. Going from 36 to 108 is adding 72. That seems like a big jump. So I'm thinking this is not going to be quadratic because I can tell going from 8 to 24 is 16, and going from 24 to 72 is 48, that is not a constant difference. So it's not quadratic. Let's check our exponential. So I'm going to do 12 divided by 4 equals 3. Then I'm going to do 36 divided by 12, that equals 3. Then I'm going to do 108 divided by 36 is 3. And then I'm going to do 324 divided by 108, it equals 3. So if I have a common ratio, then I have an exponential function. So not too difficult to check. Just remember, start with linear, start with your first differences, then move on to your second differences. You just have to be able to remember which one matches with which function, which test, which check matches with which function. Application problem. So now once we decide which type of function models the situation, then we want to be able to figure out how to write the actual equation for that function. The owner of a framing store tracks the cost of bubble wrap for packing pictures like the one shown. How can you use the data to estimate the cost of the bubble wrap for a picture with a length of 75? So here's the data we have. For 6 inches of bubble wrap, it costs 10 cents. For 12 inches of bubble wrap, it costs 31 cents. For 18, so let's check our change in X. So our length is going to be our input and our bubble wrap will be our output or our cost. So we're changing by 6 each time. Okay, so we go up by 6. That's constant, so that's fine. Let's take a look at our first difference. Going from 0.1 to 0.31, that's a change of 0.21. The next common difference is 0.31. So again, you're just taking the second number and subtracting the previous number to find the difference. The next difference is 0.42, and the next difference is 0.53. So not constant, it's not linear. So then let's move on to checking for quadratic. Check the second differences. Going from 0.21 to 0.31 is a common difference of 0.1, or a second difference of 0.1. The next difference from 0.31 to 0.42 is 0.11. That's pretty close. And then from 0.42 to 0.53 is also 0.11. That's relatively close. That's close enough. So let's say that this is a quadratic model. Okay, the common differences, the second differences are pretty much the same. So now we need to figure out how to write the equation for the quadratic function. So if you remember, our quadratic functions are written ax squared plus bx plus c. What does c represent? Our initial value. And we need to know what goes in a, b, and c. Now, can you think, what tool have we used before where we could get values for a, b, and c in our quadratic equations? We did that in the last lesson when we were doing our quadratic regression. So now that we know it's quadratic, we can go do a regression with our data table and get the equation. So on your graphing calculator, we're going to type in our list, go to stat, then edit. Remember, length is our x value, so that's L1. You just type in 6, 12, 18, 24, and 30. List 2 is our y values, and you're going to type in the cost, so 0.1, 0.31, 0.62, 1.04, and 1.57. Make sure your lists match up. You have the same number in each column. And then we're going to do stat, arrow over to calculate. We're going to calculate the quadratic regression. So type in number 5 for quadratic regression. Enter, enter, enter. If your diagnostics are on, you should get your R value. And we can see, remember that's our correlation coefficient for quadratic function. It's very, very close to +1. We know this is a good fit. So now we have our values for A, B, and C, and we can type those in. You can just do a couple decimals, 2 or 3 would be good. So then substituting those values for A, B, and C, we can write the function 0.0015 x squared plus 0076x plus 0.002. I ran out of room. So there's our function that represents this situation. So we have one more step we need. We need to estimate the cost for the bubble wrap when the length is 75. That means what's our input? When x is 75. So we have an equation, we can just plug in our value. So we're going to evaluate f of 75. Plug that into your equation and calculate. So we would do 0.0015 times 75 squared, etc. Okay, I'm going to run out of room. So substitute 75 for x in our equation. And if we do all those calculations, we should get a value of $9.01 to bubble wrap a picture with a length of 75 inches. Try it number 2. First, we need to determine what type of function this is, if it's linear, quadratic, or exponential, and then use regression to write the equation to model the data. So let's check. Going from 100 to 89.5 is a decrease of 10.5. Going from 89.5 to 78.9 is a difference of 10.6. We lose 10.6. Going from 78.9 to 68.4, we lose 10.5, so pretty close. Thinking this might be linear. And then going from 68.4 to 57.8, we are losing 10.6. So it looks like we have a common first difference. That means it's linear. So remember, linear functions are written y equals mx plus b. We need to have value for m, the slope, and a value for b, the initial value. So you might just be tempted to put in negative 10.5 as your rate of change as m, but it's not constant. It's not technically exactly constant. So let's use our graphing calculator, type in our lists, and do a linear regression. We're going to do the linear regression option now. So on your graphing calculator, go to Stat, Edit. We need to edit our list, so I'm going to clear it out. Go up to the top, hit Clear and Enter. 0, 1, 2, 3, and 4. Clear out the next list. Clear and Enter. And I have 100. I have 89.5, 78.9, 68.4. and 57.8. So something to remember, in real world situations, things aren't going to be perfectly linear or perfectly quadratic. We're looking for something that best fits, best models the data. So we can't just say, hey, the change was about negative 10.5. We want to be accurate. So that's where our graphing calculator tools can be useful. So we have our lists in there, and then remember, we're going to go back to Stat, Calculate. This time we're doing a linear regression. Option number 4 makes it look like y equals mx plus b. So I'm going to do that. Enter, enter, enter. You can see the r value, the lowercase r, is pretty close to -1. That means it's a near perfect, very close to perfect negative association. So we have a good number, and look at the rates. The rate of change is actually negative 10.55, and look at b, look at the initial value. It is 100.02. So a little bit different than what we have in the table. So if we substitute those values in, our rate of change was negative 10.55 according to our calculator, our linear regression, and the initial value was not 100, it was 100.02. Example 3, comparing linear, exponential, and quadratic growth. So we did this when we did exponential growth, we compared it to linear. So then how does quadratic fit in there? Remember, we saw that sometimes linear growth is faster or gives you a higher output than exponential up until a point. There's a point when exponential will start to take off and overtake or be greater than linear. So where does quadratic happen? Let's look at this table of values. F represents the linear function, G represents the quadratic function, and H represents the exponential function. You can see in the graph, the X is in the exponent. Population of city C, or the green H of X, is greater than those of city A and B when we get here to 11 years. So there's a point where quadratic and linear are less than the exponential. So the linear growth is always higher than the quadratic growth. Okay, the red column is always more than the blue column, and the red column is greater than both red, blue, and green up until we get to years 10 and 11. If we were to type these on our graphing calculators, we could see, changing our scale window to 10 and 32, then we can see there's a point of intersection. And we can find where they're equal to each other, or we could find the point where the exponential growth, city C, overtakes both city A and city B. So like we saw on the table, after 10 years, city C will exceed the populations of city A and city B. So to do that, all you would do is you would go to y equals on your graphing calculator, and you would type in these three equations, and then you would just change your window here to fit the scale that they've given you. That way you could see all the way out here. Try it number 3. Compare these functions. Show that as x increases, g of x, which is our quadratic function, will exceed f of x, our linear function, and our exponential function. Okay, and then it will eventually exceed, and the h of x will eventually, the exponential will eventually be more than both the others. So we're looking for when g of x, when the quadratic function is more than the linear, and then we want to see where exponential is bigger than all of them. So get out your graphing calculators. We're going to type these equations into our graphing calculator. Going to y equals, we want to make sure first that your plots are not highlighted, because when you're graphing from y equals, your plots need to be not on. So make sure they're unhighlighted. And then we just type in these equations. I'm going to do linear first. So linear is going to be blue. 3x plus 2, hit enter. The next one will be g of x. This is my quadratic equation. 2x squared plus 3, enter. And my black line is going to be, I want to do green. My green line will be h of x, so 2, and then you're going to do this caret, and then x. And hit enter. So there's my 3 graphs, my linear, my quadratic, and my exponential. Where is quadratic more than linear? We can see there's 2 intersection points, right? So I'm going to zoom in a little bit more. Let's see right here. Okay, you can see it crosses and linear, and then it's more about just over where my cursor is. So there's a point there, about, so we can calculate that intersection. So second, calculate, intersect. There's my first curve is the blue one, enter. My second curve is the red one, yes. I want them to do this intersection point. Oops, let's try again. Second, calculate, intersect. Yes, my first curve is the blue one. My second curve is the red one. Yes, that's where I want it. So they intersect at 1, 5. Okay, so that's where the quadratic would be more. And then, I'm going to zoom back out, zoom standard. When is linear and quadratic going to be less than ? They're still greater than. Let's zoom in one more time. Oh, getting closer. Calculate the intersect. Let's do, the first curve is linear. The second curve, I want it to the green curve. So at 3.7, 13.15, then it will be greater than, because that will exceed. And then let's do, calculate the intersection of the green curve. So my first curve is the red one. My second curve is the green one. Now let's see. That intersection is at 6, 85. So yes, eventually the exponential function will exceed both of them. Made it to the concept summary for linear and quadratic and exponential functions, how to check which type of function the data is. So always check your first differences first, then move to your second differences, and then check your common ratios. And just remember what each graph looks like And remember that exponential will start to exceed both linear and quadratic eventually. There will be some point where that is increasing faster than anything. If you have any questions, put them in the comments. Make sure to like and subscribe. Come back for topic 9.